Okay, so thank you so much everyone for coming. This is amazing. Thank you very much to all my students, to my dear friend Manpreet, who's coming from UCSD. Thank you so much for being here. And I think we're all excited to hear about Lucia's research. Lucia Praticò is a doctor now, or she's going to defend very soon. So she's going to turn into a doctor very soon. She did the bachelor and master in Italy, the University of Bologna, this beautiful city, and the PhD as well at the University of Bologna. You know that this is the oldest university in Europe. It was founded in 1088. So it's the oldest university that we have in Europe. It's a beautiful city, and today she's gonna talk to us about a little bit about the city and more about the research that she did during the PhD. So thank you again for being here. Let's hear to Lucia now. Thank you so much. Okay, I would clap.
Okay, guys, so nice to meet you. I am Lucia Praticò from Bologna, and thank you, Gloria, for this. Thank you, Jose, for this talk. I'm very happy to be here. I did my PhD research in the School of Engineering in Bologna, in structural engineering. I just put some nice pictures of the city here. These were taken by a friend of mine. This is the city center of Bologna. You can see like the main square, the main church, the porticos. It's very nice to walk around. We don't have a campus as the one that you have here, but the university, the faculties is spread all over the city, so you can just walk, enjoy the city, and then you will find your faculty. It's pretty old, as Gloria said. So I spent like many years here to study. I'm not from Bologna, but it was nice to live as a student in the city. It's very energetic to stay there. And I spent the last 3 years, in particular, working on my PhD research with Professor Marco Savoia and with engineers Marco Bovo and Nicola Buratti, working on this main topic, which is the evaluation of seismic losses concerning precast reinforced concrete buildings. And today I will talk a little bit about the case of the industrial areas after the 2012 Emilia earthquake in Italy. That was pretty important for us and for the development of structural research. So first of all, I don't know your background, so I've just put some introduction, okay, to the topic and to let you understand better the aim of my research and why we address this problem. First of all, talking about the seismic risk. Seismic risk is conceived as the product of seismic hazard, vulnerability, and exposure. Talking about hazard, actually, it is this is the problem of quantifying the seismic action. Okay, and you may know that it depends on, of course, the location of your building. It depends on the site, so the faults that you have in your location and the activity of these faults. Engineers mainly work on the vulnerability part, which is like, to let you have an idea how the building is behaving under seismic actions. So there may be more fragile buildings, more like stronger buildings. It depends, of course, on the structural typology, but also on some local properties of your building, of your structures. And then there is the exposure, which means that it is this is the value exposed to the risk. So in this case, it can have several there can be several aspects. It can be, for example, the amount of economic losses that you may lose after an earthquake hits a densely populated area, for example. So it can be, I don't know, human losses, losses due to damage to structures, damage to non-structural contents, there may be several aspects. So as engineers, we need to quantify the seismic action, and we usually do it by considering the peak ground acceleration. So this is an example of a map of the PGA on rock in the world. And of course, the red is like the marks the area with the highest PGA, so the strongest earthquakes. The point is that the seismic risk, so the product of hazard, vulnerability, exposure, is increasing because mainly, okay, here you can see the active areas, but this is not the only problem. The other problem is that the cities and the urban development is increasing. It is getting higher, and so the mega cities are spreading all over the world, and this means that the exposure is increasing. So this will increase, of course, the risk, and we need to focus on this aspect. Here I put a map of the seismicity in Italy. So you can see some of the main earthquakes that hit my region, my state, in the last years, starting from 1908, so some very old earthquakes, to the most recent ones. So you see that there is a central area, which is like the purple one, with the highest seismicity for us through the Apennine mountain, from the north to the south of Italy. And I want to raise your attention on, first of all, on this site up here, which is Istituto Nazionale di Geofisica e Vulcanologia, which is our reference site for the quantification of the seismic action in Italy. So usually we take the measure of the PGA, the peak ground acceleration, from this site, so we have an idea of the shaking intensity. Moreover, it is important to see that after this earthquake in 1980, which is the Irpinia earthquake in South Italy, like here, close to Naples, the civil protection system was set. So basically, this is an organization which is very important for us. It's part of the government, which is trying to understand and to quantify the seismic risk in Italy. So as well as other sorts of risk, like we have floods, we have also some problems with the wind in some areas, but mainly one of the main natural hazard is earthquake for us. So we're really interested in understanding what is the risk for our built environment and, of course, for people. And we usually refer to the civil protection for the organization of the aftermath recovery in the post-earthquake situation, and also how to deal in the emergency situation. We usually refer to this system. And it is thanks to this that the Italian universities in the network called ReLuis, you can search for it, they are working together trying to develop an updated risk map of the entire state, so involving all the regions, and that should be updated with the latest events and ground motions that we know, that we experienced. Okay, so in this is the same map, but with an indication of the losses. So in Italy, when we experience an earthquake, the government is setting all the funds for the reconstruction process of the buildings, of the infrastructures, and also to fund all the victims, for example. But also it is managing the like the homeless and all these communities problems. So here you can see that we try to put a measure on the amount of losses, and there are some core earthquakes, like the Emilia one, that is like here in the north part of the country. We experienced this earthquake in middle Italy, which is quite recent, the most recent one, and there were like many victims and many losses, monetary losses that you can see. But then there are some of them with like this one, which was quite old, but with a huge amount of losses. So in this like 50 years period, the total number is 500 victims and 1,000, sorry, and a huge like billions of euros of economic losses that the state has to pay for the reconstruction process. And the same are plotted in these histograms that you can see here. So we actually, the government is raising the awareness about this problem, because we don't have like all this money to spend for the reconstruction after the earthquakes. So we need to work on the retrofit of the existing buildings in Italy, because you may know that we have several ancient buildings that we don't want to demolish and build again because they're part of our culture. And many buildings are quite also many of the civil structures are quite old, and we really need to understand which are the most exposed towns in our country, and try to focus on the buildings and the infrastructures that need to be protected and also retrofitted for this problem against the seismic action. So this just an introduction of what I did. So as you understood, what we did about risk, it's actually a multidisciplinary problem, because you have to, you should evaluate your the risk of the seismic risk in your area for your building, knowing both the properties of your building, but also the hazard of the site. And you should be able also to make a quantification on the values that are exposed to the risk. The result of the risk analysis is the evaluation of the seismic losses, the economic losses. So everything finally will be converted to money, to understand the value, the different value of the assets that are exposed. It is very important to evaluate the seismic losses. So both for to forecast possible scenarios, so to understand what can be your the losses, the amount of losses in an area compared, for example, to another which is closed, for example, which can be subjected to the same ground motion, but maybe have some stronger buildings. So there may be very different losses expected. Moreover, it is very important for the government and for the civil protection, for us, to decide policies and to organize the allocation of funds, both for the retrofit of the existing buildings, both in the reconstruction phase and the recovery phase after the earthquake. So some examples of the losses. Losses is actually, you have to imagine it is a broad term. It is including some direct losses, so due to the repair of buildings, of the structures, but also the repair of the inside of the components, that can be non-structural assets, for example. But also there are some indirect losses that you may include in your modeling, like, for example, the business disruption that comes after an earthquake, or the supply chain interruption. So there are some very important economic aspects to be that should be considered. But there are also the social and human losses, like the number of fatalities, injuries, homeless, but also the disruption of the community, which is something that should be taken into account in a very comprehensive model. In particular, in my research, I worked on the modeling and prediction part of the losses. So I tried to calibrate models to quantify the seismic losses in possible scenarios. But also I worked in the field of the empirical data collection, which is very important. So you have to imagine that after an earthquake, there are so many data on the losses, but also on the damage, the seismic damage on buildings that should be elaborated and should be studied to define proper functions to be used in your modeling. So these are two very important fields of study in the risk topic. And then there is, of course, the decision-making phase, which is something more for planners. So as engineers, we usually give data, give numbers to decision makers to then that should be understand the problem, make decision and allocate funds and so on. So I will focus mainly on three main topics which I addressed in my PhD thesis. So two of them dealing with modeling and prediction of losses, and one dealing with empirical data collection. The first one is a large-scale scenario assessment, considering the industrial areas that are hit by an earthquake. So in this case, we consider the seismic event in Emilia, in the Emilia-Romagna region, which is my region, our region, that hit the region in 2012. And in particular, I was focusing on the seismic behavior and the damage and the losses of precast reinforced concrete buildings. In our region, there are many industrial districts where this kind of production, commercial industrial buildings are located together. So basically, there is like a town and close to it, a small industrial areas. It is pretty much like this everywhere in our region. And in these districts, there were many structural collapses after this seismic sequence. You can see an example here. I just reported a bunch of pictures. And what is interesting is that you can see that in these kind of buildings that look like this, that have some precast beams and roof elements, but also precast columns. So they are, all these elements are like manufactured, they're prefabricated. In these buildings, there are usually no rigid diaphragm at the roof level. So the roof is not rigid. So the different precast frames, they are not behaving together under the seismic action. But it is like every frame, in the majority of the cases, is working alone. So it's sustaining the size, the mass, and the seismic action alone. So what happens is that in this kind of buildings, you can see these localized collapses because only some of the frames are failing or may fail. So not the entire building, which is actually quite large in plan. So there may be this kind of failures. So you can see that these heavy precast elements may lose their support and fall down. And this was mainly due to the bad quality of the steel connectors, both between roof element and main beams, both between the columns and the main beams. So there were many collapses due to the loss of support like these, but also collapse of the roof as well, and loss of verticality of the columns like this one, and then formation of plastic hinges at the base of the columns. These are flexural plastic hinges. Moreover, there were many examples of damage to non-structural elements like the perimeter element, the cladding panels on the perimeter, which were precast as well, very heavy. And also in this case, the connection in many situations were not sufficient to sustain the mass moving with the earthquake. So there are many examples of fallen precast cladding panels and loss of verticality as well, but also fallen masonry infill walls like this one below, or out of plane behavior of the masonry walls like in these pictures. So there are different kind of seismic damage, but we can say that it is possible to classify this type of damage, and they are pretty much recurrent. And this makes our work easier because it is for this kind of buildings, it is quite easy to understand the seismic behavior because there are few examples of damage development and collapses. So what we did is we wanted to create a method in order to perform large-scale risk assessment for industrial areas with this kind of precast buildings. So we have just put a mark on different steps of the analysis, and all of them were involved in quite a lot of work, actually. First of all, we had to select the taxonomy.
If you're in 321 or 608, sign this, please, as it goes around. Have it around. Name, grade ID, and which course it is.
Can you also do it for CV625? Do we have room for everyone? Do you have an additional paper? No, you have only one.
I don't have one.
Just have the one page.
Okay, try to think everything there.
Where is that?
For my class.
Okay, lo facciamo girare. Okay, thank you, Professor. Okay, so I was saying that we wanted to define a method that was applicable to this kind of buildings. So first of all, we had to select a suitable taxonomy and suitable structural categories, because I was saying that the sections of those elements were recurrent because they were prefabricated, and we had to model all of them. So we created a classification by selecting the main structural parameters that were controlling the seismic behavior of these precast frames, and we conducted, we came out with 120 finite element models, and we carried out IDA analysis, which is incremental dynamic analysis, like nonlinear time history analysis. I don't know, you may know them, you may heard about that. What we did is we performed a huge number of analyses in order to understand the seismic behavior of this frame, these models, in order to define, finally, the fragility curves of those buildings. The fragility curves are this kind of function that have that are giving you the probability of exceeding a specific limit state, for example, the collapse, under different intensity measures. In this case, the intensity measure that we adopted, is the spectral acceleration at a given period of vibration of the frames. You can also use the peak ground acceleration, the PGA we were talking about before. So we defined these fragility curves, and we created a library of coefficients, which is like something, a parametric way to define the fragility curves, which is allowing you to say, okay, if I have a portfolios of buildings, I can just use this library. I can define for each building a classification, identify the class, and then I will be able to find directly the fragility curve. So it's a tool specifically developed for precast RC buildings to define quickly the fragility curves. So this was the aim. But how could we know if the curves were reliable or not? We did an application of a seismic scenario to see if it was possible to find reliable results, knowing a specific real situation. So what we did is we found an industrial area, which is San Felice sul Panaro, which was very close to one of the epicenter of the seismic events in 2012, and it's inside the Emilia-Romagna region, so up here close to Bologna and Modena. And yeah, here it's there's Cesena, which is my hometown, just to see. Okay, so we selected this area, which is the industrial area of the city of San Felice, with like 100 industrial precast buildings. And those buildings, they behaved in the same way that I've shown you before. So there were the same kind of damages to the structural elements. So we performed large-scale evaluation of the number of collapsed buildings under a specific seismic scenario, because we had a huge amount of documents on what happened during the seismic sequence on those buildings in that area. So we were able to say, okay, let's try to see if our curves can work in to provide the result of a scenario assessment like this, and to forecast the exact number of collapsed buildings in this case. So what we did is we developed a Monte Carlo analysis in order to simulate the behavior of those buildings under 3 different seismic scenarios that were all of them referring to the event of the 29th May 2012. And we knew that the exact number of collapsed buildings in that scenario was 42. So it was nice to see that with, let's say, going from a less refined to a more refined seismic input. So basically this is the quantification of the ground motion. So with a very refined model for the seismic input, we came out with a good matching with the average number of collapsed building in the area with this scenario analysis. And this is a conditioned analysis, which means that in this risk assessment, the seismic action is conditioned to the location of the buildings. So it is referring to a specific seismic event. And it was nice to see that, at least in this application, the fragility curves were able to give us good results in terms of number of collapsed buildings. And we will perform similar verification also in other industrial areas for sure in future works. So yeah, this is just an idea of what I was saying before. We also developed a more direct simplified method that can be used to obtain to handle rapid results. And what was nice is that these 2 methods were giving mostly the same outcomes. And yeah, so the goal of this first part was to try to provide a tool giving a uniform approach at the large scale for the risk analysis of precast buildings, a tool that requires few data to be used. And it was good that we found out that there was a good agreement in application of the methods compared to the real data that we got after the seismic event. Okay. So very fast, another tool that I developed for concerning the modeling and the prediction of the losses is concerning this time a time-based loss assessment on reinforced concrete buildings. So maybe it's not the same here, but in Italy, ordinary buildings like houses, offices, like residential buildings, they are mainly masonry or reinforced concrete. So this is the majority, at least. So when you, since I was saying that our existing buildings are quite weak to seismic actions, we need to retrofit them. And we developed a method to estimate the unconditioned losses. So this is why it is called time-based assessment. So to estimate the losses under several seismic action that may happen to this building in 1 year. This is the idea. In order to evaluate which kind of retrofit option can be the optimal one for a specific building. So in this case, this tool is devoted to the application of to a single building, not to a large-scale application. and should be used in the preliminary phase when you have to decide which kind of seismic retrofit, seismic intervention can be the most appropriate to your structure to lower the amount of expected seismic losses. And here we have considered 3 applications. So FRP techniques, like fiber reinforced polymers, concrete jacketing, and CAM is like, this is an Italian technique, like active confinement technique with steel elements. So basically they are quite simple interventions, but quite common, I would say, applied on mainly on the columns in frame RC buildings. So here, yeah, I have a
before they build, or this is for retrofit?
For retrofitting an existing building, yeah, because you may, yeah, like in the design phase, when you're still deciding which is the most appropriate option to go for. So this is the framework of the analysis, and it is a simplified analytical method, starting from, in this case, from nonlinear static analysis, the pushover analysis, that are implemented nowadays in every software of structural calculation. So it is this method should be, it is thought to be simple and used for should be used by practitioners, by engineers. So it shouldn't be very complex, but still able to give reliable results, at least for the comparison of the different options. This is the goal. So starting from nonlinear pushover analysis, we are basically considering the losses coming from the repair of the structural elements, the repair on the non-structural elements, but also coming from the probability of demolition of the building and the probability of collapse. So if the building survived the earthquake and has to be repaired, or if the building is like heavily damaged and has to be demolished or collapsed. This is the idea. And in this time-based framework, we come out with this term, expected annual losses, and a term which is the annualized probability of collapse. So these are these loss terms should be compared together in order to find the retrofit option that gives the lowest expected annual losses and the lowest annualized probability of collapse of the buildings, which means that your building is good, it is robust to seismic action. This is the idea. And then we evaluated some other economic parameters like the cost of the retrofit, the net present value, which is the loss after a certain life period of the structure, like 50 years, which is the one for common for ordinary buildings, and the benefit cost ratio to let you understand which is the most economically convenient retrofit option. So yeah, we just got some results for this build. I will go fast here. Yeah, so finally, the aim of this tool is to provide like a graph like this one, where you can directly compare the result of your analysis, knowing for each option, like making separate pushover analysis on different models. So you model the effect of this retrofit, of each local intervention on the columns. You run the analytical analysis, which is step-by-step analysis. It is quite simple, it's not complex. But finally, you come out with an indication of the expected annual losses, which is the amount of losses expected over in 1 year, which is annualized, the probability of collapse, but also the MBS, which is the indication of the safety of your buildings, like a safety index, and the benefit cost ratio, which is depending on the initial cost of investment that you have to sustain for each retrofit option. So if you compare these terms, for example, in this case, the CAM option, the CAM, is actually the best options for this, for the case study buildings that we evaluated, because it is able to lower the losses, the expected annual losses, the probability of collapse of the building, but with a high benefit cost ratio. So it means that you're not like spending too much money, and with a good also safety index of your structure. So looking at this graph, I would go for the CAM option for that case study building, for example. So this is the idea. I will not go into detail too much in this. And so what was the aim again is to give a tool for to be used at the design stage, not to give like the best absolute results, but to set a uniform approach for a comparative evaluation of the results. So just if you have several options, you don't know what to choose, if you just base your evaluation on the initial cost of investment and on the result of some modeling, it may not be enough. You should also make some loss evaluations, which are like in Italy, recently they developed something similar, but even more simplified actually, to try also to set the loss evaluations in the works of the engineers, because they should be quantified, they should be computed, because it is not enough if you just compute a safety index for your buildings. So this is the main idea of this work. So everything is to support the decision-making phase of the engineer, but without complex analysis. And okay, in the last, yeah, I saved some time for this last part, because here I had the opportunity to work with some important data regarding, again, the 2012 Emilia earthquake. Of course, this earthquake in particular, it hit and damaged both ordinary buildings, but I was mainly working again on the precast reinforced concrete buildings, damage and collapses. And it is important to, okay, it's important to have an idea of what happened in terms of losses and in terms of data of the damage. In particular, in our region, this is a scheme of the area, the core area affected by the seismic sequence in 2012. And you should know that in that area, there was an industrial herd that was very, very important and hosting different companies, Italian, but also international companies that were producing like the majority of the income for the area, of course, for the region, but also for Italy. So there were many industrial clusters, from mechanics to food industry, and also biomedical products. So the problem was that all these companies were working in not with unsafe buildings, unsafe reduction buildings, because those buildings were not designed for seismic actions. Because before that year, 2012, that area was considered in the national regulation as non-seismic. So we were not expecting that ground motion. So that area was producing 2.5% of the national PIL. What is good is that right after the earthquake, there was a huge loss in the gross domestic product of the area. But then, after a couple of years, the area started to grow again. And this was due to the good reconstruction process that was issued by the region. So the region was able to set a good program of fundings and was able to sustain the companies to raise again, to start working again and produce. Yeah.
What the PIL stands for.
Yes, that's the Italian.
Yeah. It's the Prodotto Interno Lordo, which is the Italian one for GDP, gross domestic product. Yeah, yeah, you're right. I have to change. Okay. So our region, Regione Emilia-Romagna, created a database that was aimed at collecting all the requests for funds for the reconstruction after the seismic sequence, and in particular those concerning the production buildings. So there was a specific decree defining all the criteria for this for the reconstruction and for the repair and the retrofit of the buildings, but also for the restoration of the products, of the industrial machineries, and the relocation of the activities. So in the entire database, this was the entire Sphinx database. It was inside. There was like 2,000, more than 2,000 industrial buildings, with all the data about damage to the structures, damage to the contents, and the losses, the economic losses, which were equal to the amount of funds to be given by for the reconstruction by the state. I created a smaller database because the point is that I had to make a process of selection from these, try to define only the precluster C buildings, so those that we have seen before. And I have created this smaller database, which is like 1/3 of the biggest one, and another smaller database, even smaller, with also some geometrical structural information on the buildings. So with those data, it is very important for us, in the field of risk assessment, to study the real data of losses, of damage on the building, because with this data you can calibrate your models. So it's so important for us to spend time working on these databases to find a suitable consequence functions. We will see them. Okay, so sorry. So first of all, we had to identify a damage scale, and from D1 to D5, you can see that the building experienced from slight damage to moderate, heavy, very heavy, and then collapsed. And we had to define also some criteria for this. So, I mean, there are some recognized criteria depending on, for example, the amount of columns with plastic hinges for the moderate damage, the amount of surface collapsed, so these kind of numbers. And yeah, I want to say that this is very similar to you may have seen these pictures that are from the European macro seismic scale from 1998. That is like one of the reference documents for us for the seismic damage scale on ordinary buildings like masonry, reinforced concrete, and I have added my own scale on precluster C buildings. So you can see that according to the regional regulations, there were also some instruction for the repair, for the retrofit of each building, depending on the damage scale. For example, D1 buildings, they said that they needed local intervention on some structural elements or entire seismic retrofit. Whereas the D5 buildings, they had to go for demolition and reconstruction, of course. So apart from the damage scale, it is also important when you create a database to have a classification of your buildings. So here there are many, there are basically 6 structural typologies concerning the precast structures, in which T1, T2, and T3, so the first 3 ones here, are the most recurrent one, the most important one. And T1 are the oldest industrial buildings and the smallest one, while T2 and T3 were the newest, in which T3 have where the newest one with the highest columns, the longer precast elements, the largest surface in plan, for example. So these are the most common ones in the region, but I can say also in other parts of Italy. So this is just an idea of the database, so of the distribution of the buildings in database. So we have to classify all of them into typology, damage scale, and here there is a conceptual map with the location of all the buildings compared to referring to these blue squares, which are the main industrial areas, and these rectangular shapes here, which are the main faults, the active faults, with in red the epicenter of the two main seismic events in 2012. So as you can see, there are some dark, some brown points here, just very close to the faults, and it makes sense because these are the buildings experiencing D5 damage, whereas the green one with the lighter damage are mainly spread all around, so not close to the faults. There are some particularities, but the majority is behaving like this, let's say. So what we have to do is looking at considering the main typologies, the most recurrent one. So as I was saying, like the 1 to 23 in this case, we have to derive consequence functions. It means that for different structural typologies and for different damage states, we wanted to define the distributions of the seismic losses, understand the mean value of this distribution, the deviations, but also all the, let's say, all the statistical parameters, and calibrate suitable functions that may adopted in your in seismic risk assessments. So these functions may be used in modeling in the models in order to forecast the possible losses, because these are based on real data. And what is interesting is that in the database, the structural costs, non-structural costs, but also the fees were categorized differently. And there were also some other voids like the insurance and the final fund given by the region, which were not always corresponding to the entire losses. There were some different cases. So if you have this distribution of the losses like this one, which is referring to data D1, so damage degree 1, like slight damage. And these are the cost in euros over a meter square. We did different, you have to pay attention when you create these functions, because in this case, since there were two different actions that the privates could go for, the losses were really different. Like you can identify a first peak here, and then a second peak of the losses here, which is like D1 regarding all the buildings that just had to do local interventions techniques on like the columns, for example, and this other group of buildings, which are the D1 buildings, so still experiencing slight damage, but with had to pay for the seismic retrofit of the entire buildings. So of course, we are expecting that these losses are higher, and we cannot just make a consequence function like this one, because it is not reliable, it is not realistic. So this is one of the issues that we had to consider, and we did it. I just reported some examples of what we did. So for each damage state, like from D1 to D5. And we came out with these curves that are, they are quite stretched, but this is the cumulative density function. So knowing this curve, if you have a specific damage state for your building, in this case for the precast ones, we are able to know which is the expected average cost, conventional cost in euros per meter square. And we are able to make predictions. So we did it for all the structural components. For example, above there are the structural ones, below the non-structural elements, and you can see that if you make a comparison of the two, of course, the structural ones have very highest values, and this was expected. It is important to say one thing actually. Everything that was like heavy structural equipments, industrial machineries, and this stuff which are non-structural, they were not included in this cost because there was a specific additional database for those, and we are still analyzing it, so we're not presenting this result. They are very important for industrial buildings. So just remember that when you deal with industrial buildings, you cannot just consider the structural losses, and this is what the majority do normally with the common buildings, okay? But it is very important to consider the losses due to the contents. In this case, these non-structural voices are just like the finishing doors and this very common stuff, which are quite poor in industrial facilities. This is why they are so small. Then, yeah, we also try to define some, also the consequence function for the most important typologies like T1, T2, and T3 at each damage state. And yeah, it is not good in this case to derive functions of the typologies with all the damage states together, because you will not be able to use this function. So this is not a good example. This is in this case. So we came up with many data. Also, we have studied the amount of the losses, the amount of expected losses against the PGA, so the shaking intensity, and also the surfacing plan of the buildings. So these are just other useful functions that you may use in your modeling. Even if I have to say that with the PGA there is a use deviation of the values, we know this issue. And then yeah, just other interesting parameters that you can develop, you can study in your database, like the insurance, the percentage use of the surface of the building, yeah, and basically the losses coming from different components, like we have mentioned structural and non-structural. There are also the fees of the professionists and these things. And yeah, just few words. In a smaller database of 150 buildings, I was able to categorize also the main structural parameters. And so there is also a possibility to know the distribution of the main geometrical and structural properties of the buildings, the construction periods, an example of the length of the beams and the roof element. So, for example, from this graph, you can see that the topology T3 is that with the newest buildings, because the roof elements become longer compared to the beams, and this is because of the advancements in the manufacturing processes. And then, yeah, the geographic orientation of the buildings, which is following the main, as expected, the main streets, limiting the areas, the two main orientations. And then we also studied, we tried to study also let's say the losses and the damage level, depending on the spectral acceleration on each building of the smallest database. And at least the average values are kind of increasing. And also the like the spectral displacement demand and the capacity on each column. So these are just some examples of what you can do with a database. So just, of course, deriving the consequence functions, but also trying to develop other important structural information that you can derive. It's very important to analyze the real data. So the goal here was to create this comprehensive database on precluster C buildings. So collecting all the possible data and analyzing them. It is something that it was not available in Italy so far. So we already had some important databases on ordinary buildings like database DADO. You can find it on the web, but it was not. It didn't have information on this kind of industrial facilities, industrial buildings. So this was very an important part of the work. Then, so yeah, it is important that we try to calibrate these consequence functions, both at different damage levels and both for different common structural typologies that can be present also in other regions, but also in other countries of the Mediterranean area. So this is to provide tools to forecast possible scenarios and of course to perform risk analysis on this kind of building. Okay, so here just, yeah, a list of other works, but it's not so important. And yeah, so finally, thank you so much for your attention. And okay, I'm happy to answer to questions if you have some.
Stop sharing. Stop sharing.
Okay. Okay. Any question?
One over here.
Yeah. Sorry?
Do you know if any of those earthquakes affected the campus structurally? Like the campus?
I didn't got it.
That's if it affected University of Bologna.
If you are
If-
any
if the
earthquake.
Earthquake.
affected your university.
Ah, sorry. Okay. Not really. Not really the University of Bologna, because yeah, it was quite close to university, but not that much. I think maybe in Modena they had some problems, but I know that here, like in this area, yeah, you can see it is quite close to Modena and Ferrara. They had some problems with the ordinary buildings, facilities, and in both cities, but they didn't experience collapses. So mainly structural damage. So to ordinary buildings, there's still some cracks are visible. I went to Modena because we did a work on schools, like primary schools, high schools. We went there for the analysis of the vulnerability of those schools, and there were some visible cracks on the masonry buildings mainly, but not in Bologna. I think it was also due to the soil characteristics. They felt the earthquake, but there is not visible heavy damage to the facility, to the buildings. Okay.
I have a question.
Yeah.
So, is this method now directly precisely retrofitted buildings in Italy? This approach?
My approach, you mean?
Yeah, or
Okay.
this approach in general?
Yeah, okay. Yeah, they some like 3 or 4 years ago now, in Italy they proposed it's called the Sisma bonus approach. We have some regulations. So they tried in a very, very simplified empirical parametric method. They tried to include the evaluation of the losses in the retrofit of existing buildings. But it's very, very simple because you have just some tables of what you expect about economic losses, and also some tables to understand to quantify the recurrence frequency of the earthquake in the time-based assessment. So it's very simple. It is, I can say, the first attempt try to pass this concept of quantify also the expected economic losses in the design. But still, this is a little bit more, it's still simplified, but a little bit more precise. So we are trying to find to develop this tool to make an advancement. So still should be still easy for practitioner, but a little bit more precise, more specific, and more reliable. Should
You see this more for seismic retrofit design, not design of a new building.
Yeah, no, not design of it. Either it should be adapted. It should be adapted. I don't know. Yeah. Yeah.
So I was wondering if you could reiterate the difference between like local, I think it was like estimated cost, like the seismic retrofit and the local losses, how like initially it's high and then like later on it's like higher. So it's like the difference.
Yeah. Like this one.
Yeah.
Okay. Like you mean?
Like what? Like I just didn't hear the difference. That's what's hoping.
Okay. Why there is a difference like this in the mix?
Yeah, like how one is like higher in the beginning and the other one is like higher towards the middle.
Okay. Yeah. No, the point is that this is a bad example of defining a consequence function in this case, because this was for damage state D1, so moderate damage, and the owners of the buildings, they could go for or local intervention on some structural elements, which is the first peak, or seismic retrofit. I can say that so we have to split the two costs to derive suitable consequence functions. But it's important to see that if you consider the local intervention, the local retrofit, the costs are much are more dense and they are lower because the average is like 50 euros per meter square. And the peak is higher also because the techniques for the local intervention are more, there are just like some of them that are pretty much used everywhere. Whereas for the seismic retrofit of the building, it depends also on the geometry of the building, on the structural elements, and there are many different ways to do a seismic retrofit. So this is why we expect that these costs for the seismic retrofit are more scattered, and the peak of the mean value is also different, is also lower. And I would say that, of course, the peak depends also on the spacing that we use.
So the different methods to calculate damage costs, is that what it is?
Yeah, there are different damage costs, not damage, but reconstruction costs. Okay, so for the, consider it just local intervention, like the concrete jacketing of the columns, the one that was shown before, or the entire seismic retrofit of the entire building, but still buildings that experience damage D1, so slight damage due to the seismic action. Okay.
So thank you so much again for coming. And,